Hello everyone. In this video, we will talk about a couple examples about using different types of cache and analyze the performance of different types of cache. So we have introduced the 3 different types of cache in the previous videos of this week. And also we need to get prepared for the quiz too. So in this video, I will go through the example problems of quiz 2. So I will use a exercise problem which is super similar to the quiz problem. Please make sure watch this video before you work on the quiz. So let me put a quick note here. So for this video, we have example problems for quiz 2. So quiz 2 is about the cache performance. So we have introduced the 3 different types of cache: direct map cache, set associative cache, and fully associative cache. So in quiz 2, we're trying to analyze the basic parameters of a cache and then the miss and hit rate for different types of cache. So we will need to have some example problem. I call it exercise 2, but I didn't actually upload this file to Blackboard. I just want to limit your workload because I basically generated exercise 2 using quiz 2. So I want to make them super similar that you could understand how to work on each problem. So my goal is now to test you as you know, everything changed. Is online and everything is online. So I actually should not call it a quiz or exam. When I give you the work, I do not ask you to time yourself. So I basically just try to give you as many examples as I can. And as long as you could figure out the solution, that will be good for your learning. It's a good learning progress. So as long as you have went through the whole process and you understand the problem, you learned it, then that's my goal. So it's not actually a quiz. So anyway, so I will use another document, and after I made the note, I'll upload that to Blackboard in the same folder of the exercise, so that you can easily use the note and watch this video to understand everything you need for quiz 2. So first of all, let's have a quick example to summarize what we have learned for different types of cache. So we have introduced the 3 different types of cache. Start with direct map cache, and we have introduced the fully associative cache and set associative cache later on. So this figure is drawn this way, but you should understand that, for example, if I have a 8-block direct map cache, and if you want to change it to 2-way set associated cache, still maintain the same capacity, then you will have 2 columns, 2 separate columns, and each of them has a tag and the data, the tag and the data. So you kind of like just reorganize the direct map cache. And if you want to have a fully associative cache, and you will have tag data, tag data, tag data, tag data, and you will have, of course, 8 ways. So 8 columns, but only 1 single row, because you have only 1 set. Because you will have only 1 set. So this is just the different ways for us to organize the cache, right? So a quick example, suppose we would like to use the direct map cache, 2-way set associated cache and fully associative cache, and always the same capacity, so 8 words. 8 words. So for direct map cache, then you will have 8 sets. For 2-way set associative cache, then you will have 4 sets, right? And for fully associated cache, of course, you will have 1 set. You will have 1 single set and 8 columns, 8 ways. So for direct map cache, of course, you will have 8 sets. So it's kind of like 8 rows, right? So, oh, sorry. I did it wrong. So it's a 4 block. It's not. So the overall number here is 4 block. So that means for direct map cache, then you will have 4 sets. For a two-way set associative cache, you only have two sets because you need two columns. For a fully associative cache, then you will have only one set, but with 4 columns. So the first example, the example is trying to map the different data in the different memory location. So in the first word, the ninth word, the first word, the seventh word, the ninth word of the memory location, and you would like to access those data in a different memory location. So what do we have? Suppose we have the direct map cache. I have 4 different rows here, and then the memory location 0, memory address 0, memory address 1, 2, 3, 4, 6, 7. So so you can go all the way up to a different number, right? But the first address we're dealing with is the first word. So the first word, the first block, and then we want to deal with the 8th block. So this is actually the 9th block because this is the first block. So the address 0 means the first block, then the address 8. The address 8 will mean the 9th block, right? So if you do, if you want to determine where they should map to, so of course the first block map to the first index, the second block map to the second index, and the 9th block will map to the first set index again, will map to the first set index again, because we have only 4 blocks. So if I do 0, 1, 2, 3, then 4, 5, 6, 7, and 8 will map to this block again. So we're doing modulus of 4, this kind of calculation to determine what kind of address should go which location, right? So if address 0 map to, the first block address, so this is called the block address. The first block map to the first set index, then of course the next block will map to the same, the ninth, so the block address 8 will map to the same location. So and the block address 6 will map to another set index, right? So we need to deal with all those different blocks inside of the memory. And then suppose we're using direct map cache with 1, 2, 3, 4 sets. So the first thing I want to access is the block 0, which is not currently. So initially the whole cache is empty. So I need to put the first thing, memory location 0, into my set index 0. So the first set, and then I would like to access the block address 8. So that will map to the same location. That means you have to kick out the memory location 0 and put memory location 8 in it. And then you find you want to use memory location 0 again. So you have to kick out the 8 and update that with memory location 0. And then you find out you want to use the memory location 6. And remember, memory location 6 will map to another location, which is the set index 2 here. So this is set index 0, set index 0, set index 1, set index 2, right? So the memory location 6 will map to set index 6. Set index 2 will need to map to set index 2. So I do not need to kick out anything because I am using a new location. So I will put that into the set index 2, and then keep the memory location memory block 0 still in the first set, still in the first set. And then we want to use the memory block address 8. So that's why, okay, I have to kick out the 0 again and put the 8 in it. So if you find, if we list the miss and hit, so each time it's a miss. So you never find anything already inside of the cache, and each time you have to go to the main memory to get that piece of data, because it is not what you want. what you want is not inside of the cache. What you want is never inside of the cache. When we try to use the block 8, then we have block 0 in it. When we try to use block 0, then we have block 8 in it. So we never have it. We never have what we want inside of the cache. You can keep updating the cache. Keep updating the cache. So this is really per. The hit rate is of course per. And then suppose we do not want to have a direct map cache. Instead, we use a two-way set associative cache. So the two-way set associative cache, originally, if I draw it this way, horizontally, vertically. So if I draw it vertically, originally I have the direct map cache look like this. And the two-way set associative cache will look like this, because you have to separate them in two columns. So each column you will have just set 0 and set 1. And originally you have set 0, 1, 2, 3. So this is two-way set associative. So that's why you have set 1 and set 0. Set 1 and set 0, right? So the benefit here is when you have set 0 and set 1, for each set you have two different locations. Each set you have two different locations. 1, 2, 1, 2, right? So each set you will have two different locations. For set 0, you have two locations. Set 1, you have two locations. And remember, we're trying to access the memory location 08, 08, 68 like this in this order. So the first time we saw the memory 0, memory location 0, I will just call it memory 0 in short. So memory 0 will need to, memory address 0, let's say address 0. So address 0 will need to map to the first set. So I can randomly pick one location from the first set. And then I need to get access to memory address 8. And remember the 8, memory address 8, right now we have to do such calculation where it should map to, because we're using a two-way set associative cache. So we need to use the block address modulus 2 each time. And that will give me the set index, right? So for example, address 0 map to set 0, address 1 map to set 1, address 3 map to set 0, address 4 map to set 1, and so even all the even number map to set 0, all the odd number map to set 1. So we're only dealing with even number right now, right? So the memory address 8 will map to set 0. However, I have another empty location in my set 0, so I'll put it here because I already took the first location of set 0, so I'll put the second number into another location of set 0. And then we need to access the memory address 0 again, and luckily we have it inside of our cache right now. When we try to use memory address 0 again, it is actually inside of the cache. So I do not need to go up to all the way down to the memory so I can get it. So I have a hit at that time. And then I need to use the memory address 6. And it is not inside of my cache. And I need to determine where should I map to. So address 6 modulus 2, it will still go to set 0. However, set 0 right now, it is full. Set 0 at this time, it is full. So you have to kick out something to put your address 6 in it. So what should I kick out? So I have just used the memory address 0. So I do not want to kick out that number because I just used that number. So seems like if something I have just used that, so I should keep it. Because it make more sense for something I haven't used for a longer time. Maybe that's not that important. So I want to kick out the memory. The data from memory address 8. I would like to kick out the data from memory address 8 instead of the data from memory address 0. So I'll kick out the address 8, the data from address 8, and I put the data from address 6 into the set 0, the second location of set 0. And then I find I want to use the data from memory address 8 just after I kick it out, and I have to use it. So There's nowhere to find it. It is not in the cache right now. It is not in the cache right now. So I will have to put it into the cache. And again, I will follow the least recently used principle. Means who is least used. The memory address 6 was used just now, and compare those two different data. The memory address 0 data is not used recently, is not used recently, because the address data from address 6, I have just used the data from address 6. So I have to kick out one thing, then I will kick out the old thing, which is not recently used. So I will kick out the data from memory address 0 and update it with the data from memory address 8. So I kick out this thing and update it with memory address 8 data. So of course, when you kick out something and you put a new data in it, of course, you do not have it in your cache, right? So you have to have miss. So we have only one-time hit when we're doing when we are using a two-way set associative cache for this example. And remember that because we are actually dealing with 3 different addresses, 8, 0, and 6, and 3 different addresses, they all map to the same set index. And inside of the same set index, you only have 2 different locations. If you are using 3 things to share 2 different locations, of course, it's not really good. So you'll have a lot of miss, because 3 different locations is not able to hold 2 different locations is not able to hold 3 different things, right? So that makes sense. And we would like to look at how about use fully associative cache. So we have only 4 different blocks. But suppose we're designing a fully associative cache, then there will be one single set, and there's no particular mapping. Requirement. So I have just 4 different blocks. They all belongs to one set. So whatever data, they will map to the whole cache. And you can randomly pick one block from your entire set. So the first thing I want to use is memory address 0. I do not have it in my cache. Initially, my cache should be empty. So I just put that piece of data into one block. And then I want to use the data from memory address 8. I do not have it in my cache. I will just put it into my cache at using another block, because the first block is taken. So I will just need to use another block. And then I want to use the data from memory address 0. Luckily, it is inside of my cache. So the green color means, oh, you got it in the cache. So you do not need to update your cache because it is already there. So you will have a hit. And then I want to use the data from memory address 8. It is not inside of the cache, but I still have some empty space. So I will put that piece of data into the third block of my entire set. And then I want to use the data from memory address 8. It is inside of my cache, luckily. So I do not need to go all the way down to the memory. So I'm able to find it in the cache. So I'll have one more hit. So this example actually shows you, well, how why we want to do a n-way set associative cache, because to use n-way set associative cache, then we are actually increasing the flexibility of the same set index. Could have multiple blocks in it. The same set index could have multiple locations, could hold multiple words in it. So you do not actually need to worry about the conflict. So however, of course, if you have a super small cache like this example, it is always hard for you to handle a lot data, right? And it is always impossible for us to do a fully associative cache. So there's a lot of things to consider for the cache design to trade off the compromise. So when we definitely want n-way set associative cache, and we do definitely want the n to be really big. We definitely want the n to be really big, and of course we also want each set have like multiple so we want the n number to be really big, and that actually means each set you could have multiple locations, right? And of course you want this number to be big, but you're not always able to do that. And again, if your cache capacity is super small, then it will not help a lot. So you have to kind of like have your cache to be a reasonable size. So you might hear that your computer has 8 gigabyte cache capacity or 16 gigabyte cache capacity. You never see some cache capacity like this, 8 words or a few bytes, right? So that doesn't actually make sense. We're just using this kind of example to analyze, to understand what does it mean for an n-way set associative cache? What does it mean for a direct map cache? So this is the example. And you all see that when we're using an n-way set associative cache, we're using an n-way set associative cache. So we actually need to update. The. So for example, 3 different numbers, 3 different address location. If you have only two, two blocks to use, or 2 locations to hold 3 different things, then you have to update. Have to kick out something and update with the new data. So then which one we select? So we, by default, we will use the least recently used principle. So what does it mean, least recently used? So such as the example we just see right now, for example, we're dealing with the address 8, address 0, address 06. So if we're, for example, we have only 2 different locations, and we can put 0 here, 8 here, and later on we find, oh, I want to use 6. And then which one should I kick out? And I will kick out the one that is not recently used. I will kick out the one which is not recently used. So the least recently used data, will be kicked out, because you have used 0, 8, and 0 again. So 0 is kind of newer. Compared with the 8. So the 8 will be kicked out, because you can only hold 2 things together. So you will determine which one, I have to kick out one thing to add a new data. So the old data, the kind of like old data will be kicked out. So you could also randomly kick out one thing. So for example, you currently have the 8 and the 0, inside of your cache, and you can randomly pick one to kick out, because it's hard actually to predict which one will be used in future more often. Okay? But most of the time, we will use least recently used. This principle, LRU, means least recently used. Okay? So you will need to note this for your quiz as well. Also, okay, so let's look at the quiz. So I made a example file. So similar to the quiz. So let's go through this file, and then you will understand how to work on your quiz. So a cache, first problem, a cache has the following parameters. Small b means block size, and we have only learned cache design. All the examples we have used till now, they have the block size equals 1. So there are cache with bigger block size. And of course, in reality, people are using that for sure. So your block size is not always 1 in reality, but you know, academic usage here, we just want to make things simple. So we want to set the block size to be 1 for most of your examples. Just try to make things simple. So number of tags, sets, number of sets. So 4 sets, and then number of ways, n way, so n equals 2, and the number of the address bits. So 32 bits are used for the address, which is typical for MIPS. 32 bits is used for the address. So in terms of the parameters described, what is the cache capacity? So how many words the cache could hold, right? How many words the cache could hold. So I have 4 sets, and each set there's 2 ways. Remember, 4 sets. 1, 2, 3, 4 sets. So 4 rows, 4 sets, right? And each set you have way 0, way 1. Each set you have 2 ways. So there are overall 8 blocks, right? Overall 8 blocks. And remember, each block is 1 word. Each block is 1 word. So the cache capacity is, of course, 8 words. The cache capacity is, of course, 8 words, right? So this is 8 words for this example. And how about if you have 8 sets and 2 ways, 8 sets, 2 ways, then you should know how to calculate the capacity, right? So the set number actually means how many rows you have, and the way number means how many columns you have. And each block has 1 word in it. Each block has 1 word in it. So it's straightforward to calculate. In terms of the parameter described, what is the number of the bits required to represent each tag? Remember, we have 32 bits address, and the lower 2 bits are always 0 because we only deal with word. And what is the number of bits to represent the tag? So within the 32 bits here, we need to also determine how big is the index. Right? The set index. How big is the set index? And that is actually depends on the set index, the length of the set index depends on how many sets you have. So we have in total 4 sets. So 4 here is the number of sets. So that actually means I need 2 bits. I will need 2 bits to represent, 2 bits to represent the set index, right? Set index. So the leftover will be 32 minus 2 minus 2, which is the tag. The length of the tag, right? So suppose the block says small b equals 1 and the set number is 8. So instead of having the set number equals 4, suppose the set number equals 8. And the n way changed to be 1 way. So it's direct map cache instead of n way set associative cache. So still there's 32 bits address. And what is the number of bits required for a tag? So the length of the tag, of course, equals 32 minus 2. You always take out the lower 2 bits because that's not used. And inside of the 30 bits left, I will need to use log to 8 because there's 8 sites. There's 8 sites. So the set index length is actually 3. So then that will tell me the tag length is 32 minus 2 minus 3, which is 27, which is 27, right? 27 bits. So that's for the first problem. Second problem is a little bit tricky, and this one is really, really important. I'm pretty sure you might see this in your final exam. So consider the load data, repeat loading the data from the following addresses using a MIPS processor with 32-bit address. So this is like a real example using the real MIPS address. Suppose we are trying to load from the following address again, and again, right? So then what is the miss rate? What is the hit rate? Suppose you are using a direct map cache and the block size equals 1. Suppose you are using a two-way set associative cache and you have 4 sides. This one you have 8 sides. This one you have 4 sides. The block size equals 1. So the capacity of the cache remain the same. The capacity of the cache remain the same. One is using 8 sets direct map cache. One is using 4 sets two-way set associative cache, 4 set, but two-way set associative cache. Right, so two different design. And what is the miss rate, hit rate? What is the miss rate, hit rate? So, and what we have to do here is, well, we need to understand where the data will map to. Right? Suppose those two pieces of data are using the same map to the same block, map to the same set for direct map cache, and that is not good because they will compete with each other. Suppose the two different data, they map to the different location, or in the direct map cache, that it will be good, right? And for a two-way set associative cache, suppose they map to the same set, and you can still hold two different things. Suppose they map to the different set, that will be totally fine. So let's check what will happen, right? So first of all, I have to understand where this will map to. So you have to do the mapping, the real mapping for a real MIPS address. So how can I do a real mapping for a real MIPS address? So here I have to write down the memory address. The first memory address, they're given in hex number. So the real binary, remember this is a 32-bit address. And then, so I will just write dot for the leading positions. And remember, the lower few bits, you have the number 2, 4. So what is number 2? What is number 4? Number 2 is 0010. And what is number 4? Number 4 is 0100. So that's the address 24. That's the address 0x10010024. So you will have a lot more bits in the leading position. I just have no space to write all of them, and it's not necessary for you to write all of them. So when I look at the address, the first address here, so I actually need to determine, because suppose I'm analyzing the first type of cache, I'm using the direct map cache, and then the lower two bits are not considered. So let's just use this color, means I do not care, right? And then I need to use another 3 bits here as the set index, Remember, we have to determine the set index. And suppose we're using the 8 sets direct map cache, and then of course I will need to use 3 bits as the set index, right? So this is the address 24. And how about the address 44? So again, 40100, right? So the lower 2 bits, they're not considered. And then I will need to use 3 bits to indicate the set index. And you find out, oh, the first address 24 and the second address, the first address 24 and the second address 44, they actually share the same set index. They actually have the same set index, right? So they have the same set index means this one maps to set 1, and this one also maps to set 1, right? They both map to the same set, and that is bad. Because if you're using a direct map cache and you keep loading this value, this value, this value, this value, this value, and they map to the same location. They map to the same location. So what will happen? What will happen if they map to the same location? So the first time you see the 24, you do not have it in the cache, so you will have a miss. And then the second time you see, the second data you see is the 44. So the 44 is not in the cache because you have 24 in the cache. So you have to update your same set with 44. And after that, you will repeat loading the first data again, and you see it is not in the cache. And then you will have to kick out your 44 and update it with 24. And then you want to use 44 which is not in the cache. So you keep missing what you want. You will never have what you want because two different data, they map to the same location. They map to the same location. So the miss rate here will be 100%. The miss rate here will be 100% because both of them map to exactly the same location. Both of them map to the exactly same location. And let's look at the two-way set associative cache. So if I want to draw a little bit detailed figure here, then I may, so where should I put it? So they set 0, set 1. So both of them map to set 1. Both of them map to set 1. So they, so you will keep updating. You'll keep updating the same location with different data, and you will never have it in your cache, right? So the second example here. So let me draw this a little bit bigger. Suppose we're using a two-way set associative cache, and still we have the same capacity. So there's only 8 different locations in this cache, but this is set 0, set 1, way 0, way 1, way 1, way 0, for example, right? And then we would like to analyze. So first of all, I still need to write down the address 24 and the address 44 in the binary. So 0, 0, 1, 0, 0, 1, 0, 0. And then how about 44? 44. So 0, 1, 0, 0, 0, 1, 0, 0. And remember, the lower 2 bits are not used. And right now we have only 4 sets. We have only 4 sets. So as we only have 4 sets, so I will need to use 2 bits. I will need to use 2 bits as the set index, right? So 2 bits are used as set index. And here 3 bits are used as the set index, So and you find out, oh, they both map to the same set. They both map to the same set, right? So they both map to set 1. So again, they both map to set 1. However, you have 2 different locations in your set 1. Luckily, you have 2 different locations in your set 1. So you will not have a conflict. You will not have a conflict because both of them can use different location with each other. So you can have this location to hold one data, this location to hold another data. So there won't be any conflict. So the first time you see the 24, and you don't have it in your cache, so of course you will have, so suppose we're, can I have a new page? Kind of like run out of space. Whoops. Return. Yeah, here we go. So what I'm doing is repeating load, repeating the load many times, right? And the first data I have to use is from 2.4, the second data is from 4.4, and the third data is from 2.4, because you will repeat this again, and then you will have 2.4, and you will load 2.4 and 4.4, dot, dot, dot. So what we are doing is load from 2.4.4.4, 2.4.4.4, 2.4.4.4, things like this, right? So the first time I see 2.4, it is not in the cache. It is not in the cache. So of course I have a miss. Of course I have a miss. So let's read this for the two-way set associative in this location. So I have a miss. And then I have 4.4, because that's the first time I see that piece of data, so I have a miss. And then I want to use 2.4, and it is already in the cache, because after you miss it once, and you will feel it, you will put that piece of data in your cache, right? So the 2.4 data is actually put in the cache, and after the second load, your 2.4 data and your 4.4 data, they are both in the cache. They're both in the cache. So the third load here, the third load here, the first load, the second load, the third load. The third load here, you will have a hit because it is already in the cache. And then you will have hit, because after that, you will have hit forever if you loop this for many times. And how about when we use the direct map cache, because we're repeating the load and they share the same location. So the 2.4 is not in the cache. The first time you always have a miss. And the second time the second load is the first time you see the data 4.4. So you still have a miss, right? So you always have miss when you first see something. And then after you access the 4.4, your cache actually is holding the data 4.4. And then if you want to use 2.4 again, unfortunately you will still miss because you do not have 2.4 in it. And then you update your cache with the 2.4, and unfortunately you want to use 4.4 after that, so you will still have a miss. So you already know what will happen. So you keep having miss all the time. You will keep having miss all the time, right? So the big problem here is how many load you want to do, right? Suppose we want to loop this. So this is the first loop, and this is the second loop. Suppose you want to loop this many times. And of course, your first time miss is a really small issue. It doesn't really matter because you want to do it many times, right? So for this example, suppose I ask you, if I want to loop this many times, even like higher than 1 million times, then I do not really worry the first time. So this miss rate will be, of course, 100%, right? Of course, 100%. And for this particular example, if I want to loop this many times, so my miss rate is almost 0, because the first miss will be super small later on after I use it for 1 million times. So the overall is almost 100% hit. The overall is almost 100% hit. But if you are using this, if you are looping this load for only twice, so then you only have 4 loads. You will only have 4 loads, 2.4.4.4, 2.4.4.4, right? And then you know how to calculate the miss and hit. You know how to calculate the miss and hit. Okay, so that's for your quiz. All right, so I think if after watching this video, everybody should understand how to work on your quiz, okay? So I will upload this file to the same folder of your quiz. All right, we'll stop here for this week.